In this section, we're going to talk about some inequality theorems that specifically have to do with triangles. And the first one is called the scalene inequality theorem. And it says that if you're given triangle ABC, AC is less than AB if and only if. Well, let's see what we can put in this blank. Let's first draw the picture. Let's do A, B, C. We're going to use this one for the definition. And then we'll use this one in the proof. So notice that the distance or length of AC is less than the length of AB. That's good. So let's call that, we'll put a notch there and put a double notch here. Well, what does that mean for the opposite angles? The angle opposite AC would be the angle B. The angle opposite this side, AB, would be the angle C. I'll put two arcs on that one. Okay, so that's a good setup. Well, notice, this side is shorter than this one, and its opposite angle is smaller than the opposite angle of AB. And that's what the theorem states. AC less than AB means the measure of angle B is less than the measure of angle C. The opposite angles. Okay, well, before we go into a proof of that, I do want to state a theorem. It's basically this theorem, but with the isosceles case. Isosceles case. In that case, if we have AC equal AB, two sides equal means it's an isosceles triangle. If that's true, well, that is true if and only if the measure of angle B is equal to the measure of angle C. That's the isosceles case. So really for this theorem, we're going to assume that it's not the isosceles case. So either one side is bigger than the other or the other side is bigger than the first. All right, let's get through this proof. Since that's if and only if, the double arrow means we're going to have two cases. This implication, and then that direction is called the converse. So the first one is, assume the left side true. Assume AC is less than AB to prove that the measure of angle B is indeed less than the measure of angle C. So here's how we're going to do it. We're going to use this triangle over here, label it the same way. All right, first step is we have to find a point D on the line segment AB such that AC is equal to AD. Here's AC, that length is equal to this length AD. So go out to right about there. May not be perfect, but it's close. So now we have that side and that side with the same length. Notice this notch isn't the length of the whole side. This just represents from A to D. Now draw CD, the line segment. And notice, as we'll note in another few seconds, that we have an isosceles triangle here, two equal sides. So let's label ACD and angle CDA as angle 1 and angle 2 respectively. So ACD, that's going to be 1, and CDA is going to be 2. And we know something about those angles already. But first, the point D exists on this line segment where AD is equal to AC by a theorem that we looked at recently called the segment construction theorem. We just constructed a segment of the same length as this on AB, which is a longer segment. Okay, so we have an isosceles triangle. By the isosceles triangle theorem, we know that the measure of angle 1 is equal to the measure of angle 2. Okay. Next, by betweenness, the definition of betweenness, we know that the measure of angle ACB is going to be greater than the measure of angle 1. That's easy to see because the angle 1 is contained completely inside of angle ACB. All right, and next, by the external angle inequality for triangle CDB, this triangle right here, CDB, we have that the measure of angle 2 is greater than both of the opposite interior angles of this triangle. This one and this one. We only care about this one, the measure of angle B. And to finish up this case, we're going to use all of these facts for the conclusion. From 2, 3, and 4, we obtain that the measure of angle B, remember we're trying to prove that it's less than the measure of angle C, and we'll be done with this case. Well, we know that that's less than the measure of angle 2 by this case, part 4. Now the measure of angle 2 is equal to the measure of angle 1. That's from this case, part 2. But angle 1 is less than the measure of angle ACB. That is by this one, part 3. But what is ACB? ACB is simply the angle C. That's equal to, I'm going to put the equals down here, the measure of angle C. So it looks long and drawn out here, but we proved that the measure of angle B is less than this, which is equal to this, is less than this, which is equal to the measure of angle C. So the measure of angle B is less than the measure of angle C. That's the end of our case 1. Case 2 is the other direction. We're going to assume this is true to prove this is true. So assume that the measure of angle B is less than the measure of angle C to prove that AC is less than AB. Well, we're really just going to use case 1. By case 1, if you relabel the letters and you use AB less than AC, you will get that the measure of angle C is less than the measure of angle B. So measure of angle C is less than the measure of angle B. That's a contradiction because we assumed that the measure of angle B is less than the measure of angle C. Contradiction. So that case is impossible. The only other possibility is that AB is greater than AC. And that's exactly what we wanted to prove. I did write it the other direction, that this means AB is greater than AC. And that's the end of that proof. Now to finish up this video, we've got just a corollary. It's actually a 3-part corollary. We'll call it a corollary of the scaling inequality theorem. So we'll call it scaling inequality. And this is pretty trivial. The longest side of a triangle with a right or obtuse angle, the longest side of a triangle that has a right or obtuse, remember what obtuse means, greater than 90, is the side opposite the right or obtuse angle. I'm going to use that for my shorthand, right or obtuse angle. It just means right means 90 degrees. Obtuse is greater than 90, so I'll put greater than or equal to 90-degree angle. So the side opposite that angle will be the longest side. The hypotenuse of a right triangle is longer than either leg. Remember, the leg, that the two legs are the two sides of a right triangle that are not the hypotenuse. And lastly, the shortest segment joining a point to a line. Well, let's think about that. You got a line, there's a point. What's the shortest distance from this point to a point on that line? It would be this perpendicular segment. So that's what goes here. Perpendicular segment.